We are here today to finally discuss hardcore networking. I guess that's you're all familiar with networking. Who attended the session last year? Oh, very, very few. Okay. Okay, very good. So let me introduce myself. I'm Jerome. I'm a product manager in a network and security business unit. And I present today with my colleague Pooja.
Hi, everyone.
Hello. And so, yeah, we are today talking about logical routing. Yeah, I have to show this disclaimer slide. Our lawyers mandate it. But so, what will we discuss today? So, I have a few objectives for you, in fact, today. So, I want to make sure that you understand all the different components involved in the logical routing and how they interoperate with each other. Who has already deployed NSXV today? Quite a few. Okay. Okay. So in addition to all the different components, I will explain you how high availability works with for all those components. And finally, we'll see how do we put all those things together. What is our recommendation in terms of deployment. So all those points will be about NSX for vSphere. But in the second part, Pooja will present NSXT today. And we will do that through a demo. So first part will be really theoretical. And we'll discuss, focus on NSX for vSphere. So bear with us. We are presenting the 2 editions of NSX today. So short introduction. What does NSX provide you? NSX is a network virtualization solution. It's providing you layer 2, switching, layer 3, routing, NAT, load balancing, firewall, even endpoint monitoring, VPN, IPsec and SSL VPN, DHCP, server, and connectivity to your bare metal servers. Today, this session will focus only on the routing front. That's the only thing that we will focus on today. So let's look at how it works. So the very first component for the logical routing in NSX for vSphere is a distributed logical router. And even the distributed logical router got 2 different elements. So the very first element is the real true distributed object, which is a DLR instance. So that's the small router that exists in each and every of your hypervisors. That's in kernel, that's not a VM, doing this exact function. So that's a real router. Here, that we are enabling on each and every of your hypervisors as soon as you deploy it. So, and you have what we call different interfaces. We call them leafs. So leafs are basically your distributed logical router ports where you connect your logical switches, where your workloads, your VMs are attached. So usually each leaf got an IP address, and that would be the default gateway for your VMs. The second component of the distributed logical router is a DLR control VM. DLR control VM is here to handle the dynamic routing protocol. Why do we have that? Why do we have this control VM? The point is that we still want to learn dynamically routes and advertise routes that are of all the subnets that you've connected on your DLR. So the point is that as the DLR instance is fully distributed, it's present on each and every of your hypervisors. It would be very difficult to scale if each and every of your hypervisor would have to do SPF or BGP with your fabric there. So in order to avoid that, we are centralizing the dynamic routing protocol on the DLR control VM. So that's where we are doing OSPF and BGP, basically. And I will explain in more detail how does it work. Second component of the logical routing in NSX for vSphere is the Edge Service Gateway. Edge Service Gateway, this time, it's not in kernel. It's really a VM that you deploy. It's deployed through NSX. And the lifecycle is managed like all the different NSX components. So what is the goal, what is the role of this ESG? That's how we used to call it, how we call it internally. So this Edge Service Gateway, the first role is the on-ramp, off-ramp with the physical world. So it's basically connecting all your VMs that are in what we call the logical space, so connected through an overlay protocol, VXLAN for NSX for vSphere, and bringing connectivity with the external world. Your fabric, and of course beyond that, your data centers and internet and all those things. So that's the very first role of this Edge Service Gateway. It's also handling dynamic routing protocol, so we can do static routing, OSPF and BGP. So it's doing it towards your fabric and also towards the DLR. And it's also where we implement all the stateful services. So stateful services being a perimeter firewall. That does not mean distributed firewall. That's really the perimeter that is really on the edge. So really, if you want to protect your logical space towards the physical space, that's also where we implement NAT, load balancing, all the VPNs, DHCP server, and the DNS forwarder. Let's look at how do we put all those elements together now. So here I put a small logical view here of a typical deployment. So you've got two different logical switches here with one VM each, and they would be connected to the distributed logical router. And this DLR is connected to an Edge Service Gateway, and itself being connected to the rest of the world. So that's logically how it looks. In reality, if you look in the physical view, that's quite a bit different in reality. The point is this simple DLR that shows up on my logical view is implemented on each and every of the hypervisors that I've got on my topology. Here I've got 3 simple ESX hosts. So we find exactly all those leaves that exist on my DLR on each and every of those hosts, in fact. And we see that the DLR control VM is on the same network as the ESG to be able to exchange information there. So that's really, fully distributed. That's really the main point that you have to remember on this slide. Despite the fact that it's a single entity, the controller, NSX controller manages the fact that we distribute this information on all your hosts. So how do they interact together? So again, same thing. The focus is really on the DLR because the Edge Service Gateway is a router like you know it. It's just a VM doing routing and stateful services. So we assume here in this slide that the Edge Service Gateway is already deployed and configured northbound with a routing protocol. One is that how does the DLR works? So we've got a user that is configuring a new distributed logical router. So it's using UI or API towards the NSX manager. And from there, the manager will push information to the controllers. And the controller will push on each and every of your hypervisors the leaves, all the interfaces of your distributed logical router. We are using the controllers to do that and not the manager directly because the controllers are really, that's the role of the controllers to distribute this information and know where is which switch and on which hypervisor do we have to push that. At the same time, the manager is deploying the DLR control VM because as its name mentions, it's a VM. So we have to deploy this VM, contrary to the DLR control VM where it's just in kernel. As soon as this is done, the user is configuring a dynamic routing protocol here. So to learn information from the edge, which itself learns information from the external world. So we are setting up this dynamic routing protocol between the control VM and the edge to be able to learn there and advertise our potential directly connected subnets. The point is that from there, we have not pushed any information to your hypervisors. So the hypervisors needs to know all the network that he has learned from the edge. So it's pushing that toward the controller cluster. And the controller cluster, again, push it back to all the hypervisors. So here, it's pushing really the fib towards each and every of the hypervisors. So you see that it's happening, in fact, in 3 steps. Learning the route from the edge toward the control VM, that is really running the protocol, pushing the routes to the controller cluster, and pushing it back to each and every hypervisors. And from there, now we've got full communication, and so we can really communicate with the external world from there. Of course, we are a technical session, so there's no real true technical session without a packet walk. So let's see how it works. In this example, I'm showing it the 2 VMs on the same host. For a matter of time, I'm only showing that. I know that in the previous years we have shown on different hosts also. But yeah, we want to leave some time for the demo for Puja, so I have to cut some slides. So we've got VM1 who wants to discuss with VM2 here. So we assume that VM1 already knows as ARP for its default gateway, so it has its ARP table up and running and already populated. So it's sending a packet with its source MAC, its own source MAC, and the destination MAC is the VMAC used by the DLR, which is the default gateway for this VM. And of course, source IP is a VM1 and destination IP is VM2 here. So the packet is sent over the wire, or this logical switch, a green logical switch, and received by the DLR. DLR will do first a lookup for the destination IP. So destination IP, it will know that, oh yeah, it's directly connected to me through the red subnet and red leaves. So I know at least that. But now I need to create a packet to send it over the wire. So from there, I will look at my ARP table because I need to know. So here we suppose that the ARP table is already populated. Otherwise, it would ARP for the MAC address of VM2. Here it's already populated, so it gets that, okay, VM2 got MAC2, and now I can send a packet over the wire there. So source MAC would be the VMAC, and destination MAC would be MAC2 in this case, contrary to what it's showing in the slide. Sorry for that. And of course, same source and same destination IP. And from there, VM2 will receive the packet. The point that you cannot see on the slide, that you would see only if we use 2 different hosts, is that we always do routing closest to the source. That's always the case. We do this lookup would always be done on the ESX closest to the source, where the VM1 is, and not if VM2 would be on another ESX, we would deliver it directly on the red logical switch. So I guess that now you see how routing is done. But of course, all my diagrams have shown a single DLR control VM, a single DLR, a single edge. We don't want that. We want to make sure that we take into account any failure. bugs can happen, VMs can go down, host can have a problem. So how does that work? I take the example of the edge node. That's exactly the same principle that apply for the DLR control VM. For DLR, we don't need HA as such, because DLR is directly in kernel in each and every of your hypervisor. So if your VM is down, most probably it will not, or if you've got any problem of your host, the DLR will go down with your host. But all the other instances of all your other hypervisors will not be touched. It's a fully distributed system again. So that's really for the VMs that are centralized place where we really need HA. So active standby on an edge node, for example, an edge control VM, it's exactly the same. So how does it work? So we are exchanging keeper lives on a dedicated HA interface. That's pretty important there. Don't try to overload this interface, this HA interface. We are sending keeper lives, and if you use it for northbound traffic or for any other traffic that will really overload the interface, you may have issues there. So it's pretty important to try to keep it dedicated when you will deploy it. So we are changing the keeper life to make sure that's active and standby can communicate with each other. Over this interface, we also synchronize all the stateful services to make sure that the standby can take over the services. So what are we synchronizing? We are synchronizing the load balancer information, all the sessions. Same thing for NAT. We are synchronizing the NAT sessions there. So it's not only the keeper lives running there. And we are also exchanging the FIB information to make sure that we can do NSF. So now let's see what is happening when there's a failure on the active. So active is going down. Of course, it will stop answering to the keeper lives. It will stop sending keeper lives. So the standby will say, okay, I'm not receiving keeper lives. For that, you've got a configuration parameter that is called a dead timer. So after this dead timer, it's waiting for the dead timer first, of course. And when the dead timer expires, the standby will consider the active not reachable. And it will start the process to become the active. So now, the standby, dead timer is expired, the standby will try to become the active. So before doing that, it will still probe on all its interfaces to make sure that the active is really not reachable. The goal is not to end up in split brain scenario. And if it does not receive any answer, it will send a GARP. Now it will say, okay, I am taking over all the IP addresses that are on the active. I will take them over. So I need to let the fabric, all the other DLR, and all my neighbors, that the IP is moving from the former active to myself. So we are doing that through a GARP. And as soon as the GARP is sent, it's considered active. Now, the former active, so the faulty VM here, is coming back. When it's coming back, it will start in standby mode. Because what we don't want is that when the former active or the faulty VM is coming back, we don't want yet another disruption to move the active back to the faulty VM. That would disrupt the traffic yet again, and we want to avoid that. So we are only in non-preemptive HA mode. So it will not take over. It will stay as standby and exchange keeper life again. I forgot to mention there are a few questions. We'll keep it to the end if you don't mind, because we have a packed agenda and I want to leave space for Pooja. But all the questions will be welcome at the end, and hopefully we'll have time. And we will stay at the end of the session for any more questions. So now let's look at our topology that I already presented you. So how will it work here? So we see that we've got, so that's a typical small size deployment. You don't need bandwidth, you don't need anything special. Active standby is just fine for you there. And so you are deploying active standby edge nodes and active standby DLR control VM here in this case. So why do you want to deploy these kind of things, of topology? It's first because you need stateful services on the edge node. We only support stateful services if we are in active standby mode. There's another mode that I will present just after. But if you need stateful services, NAT, load balancer, DHCP server, VPN, you need to be in active standby. There. And in terms of timers for your dynamic routing protocol that you're running with the physical router and with the DLR, we need to give it time to make sure that all the different steps that I presented in the previous slide have time to happen. So we don't want OSPF to figure out that the neighbor is down before the standby is ready to take over the traffic. So that's why we got, in fact, the default timers of those dynamic routing protocols here. The second HA model is ECMP. So all the edge nodes in this case are all active, completely independent from each other. And we do support a maximum of 8 ways ECMP. So we can have only 8 different next stops for each route in this case. So that's why here I put the maximum of 8 nodes. That's really what we can do. So there, how do we set that up? That's pretty simple. I mean, each edge node will have its peering, so dynamic routing protocol setup. Here I've shown everything, so everything is redundant physical routers, 8 different edge nodes, so each edge node is peering with a physical router, and each edge node is also peering with the DLR control VM in this case. In terms of timer, we are pretty aggressive timers. That's the minimum timers that we can do, 1, 3. Why? Because each edge node is completely independent from each other. So we want to detect as fast as possible any failure in this case. So here, within 3 seconds, we'll detect that there's any failure. We'll detect that the DLR control VM got a problem, or the DLR control VM will detect pretty fast that an edge got a problem, or that the physical router got a problem. There. The point is that in this case, as they are independent, we are not exchanging any protocol information between each other. So we do not support stateful services. So you cannot do NAT, you cannot do load balancer in this case, you cannot do VPN, and all those services there. But you can still use distributed firewall. Again, when I say firewall, it's firewall on the edge. It's not firewall on each and every VNIX of your VMs. So DFW will just work fine in this case because it's done on the VNIC of each and every of your VMs. That's only the perimeter firewall on the edge that would not be supported in this case. So now let's look at the failure. So first the traffic will flow. So how does it flow here? So from one VM, it will go to its default gateway, which is local to the VM. It's on each and every hypervisor, so it's local, or for sure local. From there, the DLR will have 8 different possible next stops. So it will do an hash based on the L3 information to send the traffic to one of the 8 available paths. There. So we see that one is going through edge 1 and another one is going through edge 8. For example. That's pure hashing that is done there. So statistically, if you've got enough flows, you will have the traffic distributed among the 8 different edges. And The point is that on one way, really the edge is selected by the DLR. On the way back, it's done by the physical router. So that's why you can also have asymmetric routing there in this case. And that's also why we do not support stateful services. Because we cannot ensure that traffic is egressing the logical space on one router and come back on exactly the same edge. We cannot ensure that because one is done on the DLR and the other one is done on the physical router. So on the DLR, we have control, but on the physical router, we have absolutely no control on what is done, how the hash algorithm is done, on which information, and yeah, we have absolutely no control there. So that's another reason why stateful services are not supported. Let's look at the failure. What would happen there? So failure would be detected based on the dynamic routing protocol timers. So following our recommendation, normally within 3 seconds, we would detect a failure of one edge node. And that's why in this configuration, you absolutely need to have dynamic routing protocol. Otherwise, you will never detect that an edge is going down. If you use static route, we will never detect that failure. So you absolutely need OSPF or BGP in this example. And so from there, we've got, so we will detect the failure thanks to the dynamic routing protocol, and the traffic will be rerouted. The point is that all the traffic running through all the other edge nodes will not be affected at all. It's only traffic where the hash was saying that, oh, it needs to go on edge 1, that will be recompute and go to another edge in this case. So it's only, statistically, if you've got enough flows, it's only 1/8 of your traffic that would be affected, and that will be rerouted through another edge. Okay? Just comparison of the different HA modes. So first one that we have seen is active standby, where we've got a single edge taking that handling the north-south traffic in this case, so up to 10 gig, around 10 gig traffic. We can do even better now with the new NICs. And stateful services supported. We've got a second mode, that is ECMP, where we've got way more bandwidth for the north-south traffic. So we can have up to 8 different paths, so that would be at least 80 gig, and we can do even further with the right NICs there. But we do not, the caveat is that we do not support stateful firewalls in this case. So now let's look at the deployment topologies. And those are very simple cases, just focusing on the routing. There are very detailed sessions on that from my colleague Nimish about the reference design there. So it's already passed. It happened earlier today. But look at the recording if you want more details there. So the very first one is a typical enterprise routing there. And what it is, it's exactly what I presented during the ECMP topology. It's exactly that. So we've got 8 different edges. It can be only 4 if you don't need that many bandwidth. But basically, all the edge nodes are in active mode. And you've got your DLR control VM and a DLR there. So that's exactly that. There's nothing different compared to the ECMP topology. The other one, that's really when you need to scale way more. And you want multi-tenant, so making sure that you've got different departments and they can have overlapping IPs there, and you want really to support a very high number of DLRs, and each organization got its independent routing environment. So in this case, what we would have is still a DLR, but we will have 2 tiers of ESGs. We would have a first tier that is really dedicated to the tenant, where if they've got overlapping IP, so that's typically the model on the left, where we would do NAT. So that's why the edges there are in active standby to do NAT there. And so we would make sure that we can do NAT there. And on top of that, you've got 8 different edge nodes that are providing a lot of bandwidth north-south. So you've got 80 gigs as an exit point there for all your tenants. There. And we could use even trunks to connect more than 9 tenants there to the different edges here. You've got quite a number of deployment in this mode already. And the last one, last topology, is cross VC. So it's basically doing all the things that I presented so far, except that you do that across 2 sites, or even more, up to 8 different sites. There. I will not go into the details. I encourage you to go to this session, the NET1416BU, that is happening tomorrow morning from my colleague VMware. It's 2 sessions back to back. And he will go into all the details of this topology. There. And that's it for NSX for vSphere. Now I let Pooja take over the presentation for NSXT.
Thank you, Jerome. Mic looks okay? Excellent. So a lot of you have already been familiar with NSX for vSphere for a few years. The product released around 4 years ago and has done really well in the marketplace. Growth has been phenomenal, very, very rich capabilities. We have the network virtualization overlay capabilities, logical switching, distributed routing. We have connectivity to the edge. We have these rich services. We have API consumption. All of this is available. And NSX for vSphere has basically become the de facto network virtualization solution for all vSphere environments. Very, very rich vCenter integration, very, very tight SDDC integration with VRA and the rest of the stack. So life is good here. However, our vision as a company and as the networking and security BU is to drive NSX everywhere. So we do not want to provide networking and security services for vSphere environments only. We want to be the de facto standard for different heterogeneous endpoints. We want to control KVM hypervisors. We want to control workloads irrespective of where they are running, whether they are running in Amazon, Azure, IBM SoftLayer, whether they are running as a VM on a hypervisor, whether they're running as a container in a VM, whether they're running as a container on bare metal or a container in a cloud. We want to provide the exact same services which Jerome showed for routing for all these different heterogeneous endpoints. To do this, we have to basically decouple from vCenter. If you're very familiar with NSX for vSphere, there is like a one-to-one mapping between NSX Manager and the vCenter. So for endpoint heterogeneity and for decoupling with Compute Manager, we had to build a different edition of NSX targeted towards heterogeneous environments. And that version of NSX is what we call NSXT. The launch happened around February, and the fundamental principles are the same. You get the same common capabilities like network-based, like software-based network virtualization, distributed routing, connectivity to the physical, the edge services like edge firewall, distributed firewalling, API-driven consumption. You get all of this, but you get these for heterogeneous environments. You get this for OpenStack-based environments consumed by VIO or by Red Hat. So we are certified for Red Hat OSP 10. We work very well with Kubernetes. We just announced NSXT2.0, which will basically integrate with Kubernetes and make containers a first-class citizen of the ecosystem. So we can also deploy AWS instances. We can also deploy NSXT on AWS instances. So we get this multiple hypervisor, multiple endpoint, and multiple cloud. That's the objective. Now, since this session is focused on routing, we are not going to go into the architecture in detail, you can go and watch the recording for this session, and we'll focus the rest of our time on routing. Since you're seeing NSXT for the first time, we decided to highlight the features showing a demo. So we're going to do feature demos for all the functions which Jerome covered for NSXV, because the fundamental principle is the same. The first feature demo we'll do is distributed routing. So the packet walk is exactly going to look like Jerome showed you. Routing is going to happen in kernel. If you have two VMs located on different subnets, but residing on the same hypervisor, you have optimized routing. Traffic doesn't leave the hypervisor. And this is true for both ESX as well as KVM hypervisors. So let's go in the demo. So the demo topology which we have is we have one ESX hypervisor and one KVM hypervisor, which are prepped for network virtualization with T. The transport network is wired up. We have three logical switches. We have a web logical switch, an app logical switch, and a DB logical switch. And we have VMs attached to these logical switches on heterogeneous hypervisors. Our objective in this demo is basically to configure a logical router, which is going to interconnect these logical subnets. And the gateway for these logical subnets is going to be defined on this router. So when you look at NSX Manager, this is what the interface will look like. It's no longer opening in vCenter. This is an HTML5 based Flash UI, which you can open in any browser and log in. So when you log in, you come to this landing page where you can navigate further. We are going to go to the fabric and have a look at our KVM hypervisor, which is Ubuntu 16.04, and our ESX hypervisor, which is ESX 6.5. Both are prepared for network virtualization. We have three switches configured, web, app, and DB, and we have VMs attached to them. Now we can go and interconnect the switches by setting up a logical router. Just for kicks, we are going to call the logical router tenant1. And let's go and look at the configuration. So we've defined three logical interfaces here, the same lifts which Jerome showed for each of these logical switches. So this is for the web, the 215.81. We have the app, the 20.1, and we have the DB, which is the 30.1. So all the logical interfaces are defined. Now let's go and try to ping. So we have WebVM1, which is 215.82. Let's try to ping its gateway. Which we just defined, 215.81, so it's pingable. Again, this resides in kernel on the hypervisor. Let's try to ping another VM, the app VM, which is 20.11. And let's try to ping the DB VM, which is located on the KVM. All reachable. Life is good. So this was what you saw in the CLI. But we all like to see a graphical representation of everything and actually trace the path, almost like a packet walk to what is happening. So we have this monitoring tool called TraceFlow, where you can actually go and trace the path. So we picked a DB VM, and we picked the web VM on the other side, and we hit trace. And this is the output of the TraceFlow. So the traffic entered from the VM, hit the logical switch, went to the logical router, and was switched to the tenant web VM on the same hypervisor. Then it was carried over the overlay tunnel over L2 from this hypervisor to the remote hypervisor, to the ESX hypervisor, and then it was delivered to the switch and to the destination VM. So we just witnessed distributed logical routing across ESX and KVM. The principle is the same as NSXV. Routing always happens at source. So all the routing happened in the KVM hypervisor, and traffic was just sent over L2 and delivered to the destination logical way. Okay? So this covers east-west for heterogeneous hypervisors. Now let's go and look at connectivity to the physical, north-south routing. So for connectivity to the physical, L3 connectivity to the physical, we have two options. We support static routing and we support dynamic routing. For dynamic routing, we will support BGP. In this demo, we will basically show you how will you configure BGP and pair with the physical. Before we go into the topology and the demo, I want to introduce a couple of new terminologies which are new to NSXT. You remember when Jerome showed his two-tier slide, we had to deploy edges and create those two-tier topologies. So NSXT has the concept of multi-tenancy inherently built in, which means we can define via API two different types of logical routers. We can define what we call a tier 0 logical router, or we can define what we call a tier 1 logical router. A tier 0 logical router can basically attach to the physical infrastructure and pair with the physical. So it will typically be a demarcation of responsibility where it will be managed by your service provider or your infra admin. And you can go and create tier 1 or tenant logical routers, which are typically managed by your tenant admins or by your cloud management system. So if you run something like OpenStack, what we will be creating is we'll be creating the tenant logical router. We don't mandate that you have to build a multi-tier topology. You can just create a tier 0 router and directly attach logical switches to it. That is completely okay too. But in the demo, we will show you a multi-tier topology. The second terminology I would like to introduce is what we call an edge node. So what edge nodes are they're basically just appliances with pools of capacity for handling stateful services. So some of the stateful services which you can basically host on the edge nodes are pairing with the physical infrastructure. So we do not want to have routing on every hypervisor. We want the pairing with the physical infrastructure to happen somewhere on a centralized appliance. So the edge node is going to be the appliance where the service is going to be running. Any other service which we have not distributed today will also be residing on the edge node. So you can have NAT, you can have DHCP server, edge firewall, etc., which will be hosted on these pools of capacity, which we call edge node. The difference from NSXV is the edge nodes are available in two form factors now. We have the VM form factor, obviously, but we have also introduced a bare metal form factor for the edge node for customers who need high throughput and small packet sizes, who want to do very heavy NAT type of workloads, and they don't want to be limited by the throughput of a VM. These edge nodes are going to be DPDK enabled, so we are leveraging the data plane development kit to optimize the performance. So you're going to see crazy performance. At 100 byte packet size, you're going to see line rate with 1 CPU core. So it's going to be pretty awesome. For more details on the performance, I would refer to you to the performance deep dive by Samuel. You can go and know more about the performance characteristics there. So let's get into our demo topology. So we have this tier 0 router, which we will configure in the UI or the API. And we will host the services which are running on the tier 0 logical router on two edge nodes, edge bare metal 1 and edge bare metal 2. So we are going to use bare metal edge nodes in this demo. So the tier 0 logical router is going to establish a peering relationship with the top of racks. So I have two Arista devices here, Arista 1 and Arista 2. So we are going to have a peering relationship to both the Aristas on the uplink. On the downlink, the tier 0 is going to be connected to the tenant 1 logical router, which we configured in the first demo. The nice thing about NSXT is there is nothing to be done here. Once you attach this, we take care of all the route plumbing in NSX. So there is no routing protocol running between the tenant 1 and the tenant 0 anymore. So there is no concept of DLR control VM at all. Let's go to the next slide and look at this configuration in more detail. So I have one autonomous system. The logical space is in one autonomous system. The physical space is in another autonomous system. And remember the tier 0 edge node, the tier 0 router, we placed it on 2 edge nodes. We placed it on bare metal 1 and bare metal 2. So it's just one router object from the UI or the API standpoint, which has been tied to these 2 different nodes. So what I'm going to do is I'm going to define uplink 1 on edge bare metal 1 and uplink 2 on edge bare metal 2. Now, I have different deployment options when I tie tier 0 routers to edge nodes. I can either select active standby or active-active, just like we saw in NSXV. So we have both those models available, and in this demo, we are going to configure them in active standby. Okay? So, questions? Okay. So, let's go in the demo.
How is the routing information passed from the T0 to T1?
I will demo all of that in a bit. So we have the tier 0 router configured. Let's look at our configuration. It's in high availability mode, active standby. I have picked bare metal 1 and bare metal 2, and I prefer bare metal 1 to be active. I've already configured, sorry. Okay. I've already configured the uplinks. Let me end slideshow and see what's going on here. Sorry about that. Okay. So we were watching the tier 0 and we were looking at the uplinks. So the uplink to bare metal 1 is going to Arista 1, and the uplink to bare metal 2 is going to Arista 2. Both are configured on the tier 0. Let's go and look at the BGP configuration. So we have BGP configured. The local AS is 64530. The remote AS is 64520. These are our BGP peering addresses, one peering with Arista 1, and the second uplink peering with Arista 2. The timers are default. Now let's go and look at the Aristas to see if we see the adjacencies. So we're going to do a show IP BGP summary and look at the neighborship. So we're going to look at the first one, which is 226. Adjacency is established. Let's bring up the console to the other Arista and check the peering relationship with 238. All looks good. So we have north-south BGP adjacency established between the NSX and the physical. So now let's go and look at redistribution. So you, of course, need redistribution enabled to share information from the logical to the physical. So redistribution can be configured at 2 places. You can configure redistribution at a tenant level to basically allow the tenant to distribute to T0. Again, this is auto-plumbed by the system. And there's also a redistribution knob when you peer with the physical, so you can configure redistribution on the tier 0, right? So what we're going to do in this topology is we have, in this routing table, we have details for the routes to reach all these subnets here, they are auto-plumbed by us as NSX static. And if we had any other subnets directly connected to the tier 0, they would be NSX connected. So the source for the redistribution table are all these entries. And what we're going to do is we are going to use some prefix lists. So typically in an environment, you do not want the outside world to have access to your databases and your webs. And your apps. You only want access to the webs. So what we are going to do is we are going to do a permit web prefix list, and we are going to do a deny app and DB prefix list, and we are going to apply this route map on the tier 0 logical router. So NSXT has route maps, prefix lists, AS set, etc. already built in the platform. So let's see a quick demo. We are going to ping the VM, and the VM will not be reachable. What we're doing is from the Arista, we are pinging the web VM. It's not reachable. So we are going to go and check the redistribution. So we have a redistribution rule under routing, route redistribution. It's really easy to configure. So we're going to apply a route map here. And in the route map, we have a web app and the DB prefix list, web permit, and DB and app deny. So we are just going to go and apply this route map and enable route redistribution. So all we do is enable, save, and now the ping should work. Oops. Sorry, over here. It just went back. The ping should work. This Windows machine is just moving the mouse when I click somewhere. Let's look at the routes and see if only the web prefix was redistributed. So yes, you only see the web, you don't see the app and the DB. So this is how we do redistribution on T. Another interesting feature we have is we have BFD. So we now have BFD to physical and NSXT to help you with fast convergence. If there was no BFD, you could always use routing protocol timers to influence your failover, but we now have BFD. So we're going to tune the BFD really, really aggressive. We're going to tune it to 300, 303. So what we expect is a convergence of less than 1 second, because BFD will kick in when we'll do an outage. So let's go to the fast convergence demo and actually see BFD in action. So this is the same topology which we built. Everything is redistributed. The web VM is redistributed here. Life is good. We can introduce a failure now. So let me introduce a failure. So when we set up the BFD, we have options to set up the BFD at a global level, or we have the option to set up BFD per neighbor level. We also have the option to set up BFD for static routing. So if you're using bare metal edge nodes, for static or dynamic routing, we are going to give you under 1 second convergence, even if you have services running. So that's pretty huge for us. So let's cause an outage. What I'm going to go and do is I'm going to start a ping from the web VM to my remote desktop. And while the ping is going, what I'm going to do is I'm going to shut this interface on the Arista. When this interface on the Arista is shut, we'll see BFD kick in and trigger a failover. And we will see that the active edge BM1 will become standby. And the traffic will start going through this other path. And if everything goes good, we should only lose 1 packet. So this is my bare metal edge node 1. We are checking it's in active. So, and let's check the bare metal edge node 2's high availability status. It is in standby. Failover mode is preemptive, but you have an option to make it non-preemptive. This is my web VM. And from the web VM, I'm going to start some pings to my remote desktop where I'm running this demo from, which is 10.114.214.221. Pings are going. I'm going to log into the Arista and shut that interface we talked about. It's in interface 26, connected to HBM uplink. Let's go and shut it. I went and shut it, but the ping still seemed to be working. So it was so quick, it was a blip, you could hardly see it. So we just saw sub-second convergence. We just lost one packet in active standby mode with the NSX edge. And let's confirm. I'm going back to the bare metal edge node to see if it's now standby, because the other one is active. So this concludes the demo of east-west, north-south with route maps, prefix lists, BFD enabled, and fast convergence. We have a lot of other routing knobs on the platform, which we have not covered, but here is a list for your reference. If you want to know more about this, you can come and talk to us. We'll be at Meet the Experts at 10 a.m. tomorrow, and we can definitely wait outside and answer other questions you have. If you want to try all this yourself, you can go to the hands-on labs. We have 2 labs on NSX 18.26.01 and 02. Or you can catch me outside the room. I will show you the live setup. We can fail over and see. I was not brave enough to do it here with the bad Wi-Fi. But the Wi-Fi is really good this time. So that brings us to the end of our presentation. So let's recap some key takeaways. So NSX logical routing basically enables communication for your workloads belonging to different subnets. We have distributed routing to optimize east-west communication. We have the edges for the north-south communication to the physical and to provide network services. We have 2 modes for high availability. We have active standby, and we have the ECMP model. And all these building blocks are not just available on vSphere. We now have them available on T across multiple hypervisors, VMs, containers, and AWS. So that concludes this presentation. These are some relevant sessions and references for reading material, which or session recordings which you can go and look at. And these are some other slides which were inserted by the organizers, which talk about where you can go.
Yeah, we'll open up for questions. If you've got questions, if you can come to the mic here, and yeah, thank you.
Thank you, everybody. Please don't forget to fill the survey.
Thanks.